Alright, so in this video, I'm going to go over an empirical formula. I'm going to explain what it is, I'm going to explain how you get to it, and then I'm going to go over a couple examples. So first off, let's define an empirical formula. And just a heads up, this is the definition from my textbook. But an empirical formula is defined as the simplest whole number, whole number ratio of elements in a compound. Alright, so there's a couple things to note over here. First of all is that it's the simplest whole number ratio. So for example, you have ethanoic acid. And ethanoic acid has a molecular formula. I'll go into this in more detail, but it is a general formula um, of C2H4O2. C2H4O2. However, this isn't the simplest whole number ratio, because this has a ratio of 2 carbon atoms to 4 hydrogen atoms to 2 oxygen atoms. Its empirical formula, the simplest whole number ratio, would be CH2O, or a 1 to 2 to 1 ratio. Now, the ratio of elements isn't actually different. 2 to 4 to 2 is exactly the same as 1 to 2 to 1, except 1 to 2 to 1 is just a simpler version. So that's what it means when it says a simplest whole number ratio. The second thing to note is that it means whole number ratio, and this is a part that I personally overlooked in doing some practice. And so what this means is that, for example, if you have the formula iron oxide, except you have a subscript of 1, so 1 iron atom and 1.5 oxygen atoms. When you get to this with an empirical formula method, and this is your simplest form, well, this doesn't work because you don't have a whole number ratio. So what you do in this case is that you look at all the subscripts that are not whole numbers, and you multiply the entire equation by a number that makes these non-whole numbers into whole numbers. You want this to be the lowest number possible because, again, this is the simplest whole number ratio. So for example, in this case, 1.5 could be turned into a whole number by multiplying it by 2. So you take the entire equation and you multiply it by 2. And what that gives you in this case would be Fe2O3, which would be iron 3 oxide. But you can see that these all have whole numbers. So this would be the empirical formula for the specific formula. Alright, so now I'm going to go over the steps involved in finding the empirical formula. So the first step is to find the amount of each element in a 100-gram compound. So if you had a 100-gram sample, how many grams of each element would be in that sample? So the first step is amount of grams of each element. The second one is divide the mass of each element by its molar mass. So what this gives you is the number of moles. So if you have, let's say, an element that in a 100-gram compound would have 5 grams, it would represent 5 out of the 100 grams, well, you divide this 5 grams by its molar mass. So let's say it's hydrogen has an approximate molar mass of 1.01 or 1.008 to be more specific. But you remember the formula N, or moles, is equal to mass in grams over the molar mass in grams per mole. So this will actually give you the number of moles in the sample. So for example, in this case, it would be roughly 4.9, or more specifically, 4.95. But that's not really adding to the point. So basically what you want to do is you want to divide the gram amount Alright, so the third step is where it starts to get a little bit tricky. What you do in this step is you take the amount of moles of each element in the compound and you divide it by the element that has the smallest amount of moles. So you divide it by the moles in the element with the smallest amount of moles. And so what I mean by this is a little bit complicated. So say you do this and you have one element with, say, 10 moles, one element with 5 moles, and one element with 2 moles. So you take the one with the lowest amount and you divide all of them by that amount. And so, for example, in the case where you have 2 moles, you would divide that by 2 and you would get an answer of 1. 5 would be 5 over 2, roughly 2.5, or it would be exactly 2.5. And in the case where it had 10 moles, you would have 10 over 2, or 5. And so this would give you the general structure of the empirical formula, which you would then have to eliminate any non-whole numbers. So for example, let's call this element A, element B, element C. Dividing it by the number of moles in the element that has the smallest number of moles would give you the amount of atoms in the empirical formula. So this would be A5, B2.5, and C1. This example isn't a particularly good one because you'd have to multiply it by 2 and just get this to get your whole number ratio back, but you can see what I'm saying. But you can see a general example of what I mean when I say divided by the number of moles in the element with the smallest number of moles. Alright, so again, divide the number of moles in each element by the number of moles in the element with the fewest number of moles. A bit tricky, hopefully some examples will clear that up. So number 4 is create your skeleton formula. So like I mentioned before with the elements A, B, and C, you would have A5, B2.5, and C1. And then lastly, simply multiply the entire equation by a number that will eliminate any non-whole numbers. So you only want whole numbered subscripts. Alright, so let's go through a couple examples. So in this first one, we have a compound with 20.2% aluminum and then also 79.8% chlorine. Okay, so what will this compound's empirical formula look like? Well, luckily for us, 20.2 and 79.8 add up to 100. And so we can simply say that in a 100-gram sample, in a 100-gram sample, we're going to have 20.2 grams of aluminum, and then we're also going to have 79.8 grams of chlorine. Okay, so now the next thing that we need to do is that we need to divide the mass of each element by its molar mass to find the number of moles. So we have N equals small m over capital M. In our case, we have number for aluminum, we have number of moles equals 20.2 grams over aluminum's molar mass, which it has a molar mass of 26.98, so 26.98. When you plug this into the calculator, you get 0.7487 moles. So we have 0.75 moles of aluminum. 0.75 moles of aluminum. As for chlorine, we could do the same thing again. So this time, the number of moles equals 79.8 grams over the molar mass of chlorine, which chlorine has a molar mass of 35.45. And so this gives us 2.25 moles of chlorine. Alright, so then what we do is step 3. We take the element with the least number of moles and we divide all the moles of all the elements by that number. And so 0.75 divided by 0.75 gives 1. 2.25 divided by 0.75 gives 3. And so these are all whole numbers, so we can just create a skeleton empirical formula, and we don't need to multiply to remove any non-whole numbers because everything is whole number. So 1 corresponds to aluminum, 3 corresponds to chlorine, and we have AlCl3. And so this would be our empirical formula. Alright, so let's do one more, this time with a bit of a more complicated question. So in this one we have 50.85% carbon, 8 40.47% hydrogen, and 40.68% oxygen. Alright, so what do we do in this case? The first thing that to do is to make sure that these all add up to 100. You can do this by simply adding it up. In our case, this does add up to 100, so again, we can just use these percentages as gram units. So we can say that in a 100 gram sample, we're going to have 50.85 grams carbon, 8.47 grams hydrogen, 40.68 grams oxygen. Alright, so now what do? Again, we divide them all by their molar masses. In carbon's case, the number of moles is equal to 50.85 grams over a molar mass of 12.01. And that gives us 4.2339 moles, or we can just basically simplify this to about 4.23 moles of carbon. That's our first thing. The second one, hydrogen, N is equal to 8.47 grams divided by a molar mass of 1.01. And so that gives us 8.386 moles, or approximately 8.4 moles of hydrogen. Lastly, we're going to do the same thing again. We're going to take the amount of grams of oxygen in the 100 gram sample, and we're going to divide it by its molar mass to find the number of moles of oxygen in the sample. So we have 40.68 grams divided by a molar mass of 16 grams per mole, which gives us 2.5425 moles, which again we can reduce that into approximately 2.5 moles of oxygen, O2. Alright, so next, again, we take all the different mole numbers in this compound, and we divide it by the number of moles that is the smallest number of moles. It sounds a bit weird, but it makes more sense when you actually practice it. So let's start with oxygen, and that would have 2.5 moles over, it's the smallest amount, so we divide them all by 2.5. That gives us 1. Then we have hydrogen. In this case, we have 8.4 moles of hydrogen divided by 2.5, which gives us 3.4 as a number. And then we also have carbon, which has 4.23 moles of carbon and over 2.5. Now, something I didn't know before that I probably should have said is that there is no unit to this number. And the reason is because when you have 4.23 moles over 2.5 moles, well, the moles cancel out and there's no unit left. So this number has no unit. Nevertheless, 4.23 divided by 2.5 gives us 1.692, which we can then say is about 1.7. Okay, so let's put this all into our skeleton formula. We have C 1.7, H 3.4, and O 1. We don't really need to keep that 1 there, but it doesn't matter. These aren't whole numbers, and we need to make them all whole numbers. So what we do, again, is we multiply the entire equation by a number that'll make all the subscripts whole numbers. In this case, we can do that by multiplying the entire equation by 3. Remember that 1.7 isn't exactly exact, and so we get subscripts, so we multiply all the subscripts by this number, and we get C 5. 3.4 times 3 is about 10, so H 10, and then O 1 times 3, 3, O 3. And so this would be our empirical formula for this compound. So I hope you found this video informative. I hope it helped you out, and yeah, have a good day.